Welcome to the fourth lecture of the third week. In this lecture, we continue our discussion on computation of Jacobi symbol that we started in the last lecture leading up to the Solovay-Strassen algorithm, which uses Jacobi symbols. Now, let us recall that we talked about legender symbols. So, for legender symbols we need to have an odd prime p, and then we say that A by B is quadratic residue mod p if, well, the congruence equation y square equal to A mod p has a solution, and then the value of A by p is given as 1. So, I write over here the value is missing, okay, it is here, it is 1. If it is quadratic residue, it is 1, and otherwise it is minus 1 if it is quadratic non residue, and if A is 0 mod p, then it is 0. This is what we have studied, and we have also studied Jacobi symbol. For that, first we need an odd positive integer n. We factorize that integer like this, where pi are distinct primes and ei's are integers greater than or equal to 1. We do this, and then A by n, the Jacobi symbol, is the product of legender symbols of A with respect to each pi raised to the power ei, where I varies from 1 to p, 1 to k. All right. We have also studied a computation technique of Jacobi symbol which involved factorization of n. So, we have seen this calculation in the previous lecture. Now, factorizing a number, a large number, is not easy. The question is that can we get the same information without factorizing, and that is what we are going to discuss today. In order to do that, we will study some properties of Jacobi symbols, and in these lectures we will not be able to prove them, but we have to remember them, and they are not very difficult to remember. In fact, if you look at the first property, it is rather reasonable, and we have also talked about this property in the last lecture when we were studying legender symbols. So, it is like this, that if our starting point n is an odd positive integer, then if there are two integers m1 and m2 which are congruent to each other mod n, m1 and m2 are congruent to each other mod n, n is an positive, n is a or an odd, let me write like this, n is a positive odd integer Now then the Jacobi symbol m1n is equal to Jacobi symbol m2n. Okay, this is reasonable. The next property is interesting, and it lets us deal with let us deal with even positive integers. So, if we have 2 upstairs, then 2 by n, that is the Jacobi symbol of 2 modulo n, is going to be 1 if n is plus or minus 1 mod 8, and is going to be minus 1 if n is plus or minus 3 mod 8. This is very useful, we must remember this. Now let us look at the other properties. We come here. Now this involves product in the numerator. So if you have a product of 2 positive integers m1 and m2 in the numerator, then the Jacobi symbol will split up into products. So we see that m1 into m2 Jacobi symbol value modulo n is product of the individual Jacobi symbol values mod n of m1 and m2. This is very interesting, and we can apply this over and over again when m is 2 to the power k into t, and get this. Let me explain this a little more. This is something that we have very often. So suppose we know that n, that is something that is going to be in my denominator, is a positive odd integer. Now the integer m, which is on the numerator, it need not be odd, it may be even. Now if it is even, then I can repeatedly divide it by 2 till the other factor is odd. So that is what we will do. Let us say it is t, we will do its t is odd. Now then our property tells that if you have got m by n, this is 2 to the power k into t divided by n, this is equal to, by using the property at the top, equal to 2 to the power k divided by n, then it is t by n, and this is going to be 2n raised to the power k t by n. Now this first factor can be determined very quickly by using the second property that we discussed in the previous slide, that is the Jacobi symbol of 2 modulo n is 1 or minus 1 depending on the depending on whether n is congruent to plus minus 1 mod 8 or plus minus 1 mod 3. So, we can take care of this part in that way. And the last property, probably the most important property in this sequence of properties, is a kind of reciprocity property, which says that if you have m by n and both are positive odd integers, then you can turn them around. You can have m as a denominator and m as the numerator of the Jacobi symbol, and multiplied by a sign, and that sign is determined by the fact whether m is congruent to n is congruent to mod 3 congruent to 3 mod 4. So, here if m is congruent to n, which in turn is congruent to 3 mod 4, if it happens, then this switchover will happen with a minus sign, otherwise there is no sign, it is just switches over. Now, these 4 properties can be repeatedly used to compute Jacobi symbol of a positive integer modulo another odd positive integer without factorizing, and this is very surprising. So, let us look at the computation by an example, and I have put all the rules in one side of the slide, because so that we can refer to the rules very quickly and do the computations. So, we have the same pair of numbers 12 and 175, and I do not have to worry about the factorization of 175. So, I have got 12 here and 175 in the denominator enclosed by a parenthesis, and this is equal to. So, what I have to do is that I have to check whether the numerator integer is even or odd. If it is odd, I do not have to do anything. If it is even, then I just have to take out all the possible the factors 2. If I do that, then I see I can always do that very easily. So, if I can do that, I just keep on dividing by 2 and count the number of times I have divided by 2, and in case of 12 it is twice, 2 times I can divide by 2, and I will have the other odd factor to be 3, and I have 175 over here, alright. And now I can use the third property, which lets me factor out the symbols. So, I will get something like this: 2 square by 175 and 3 by 175. I have got this. I can do something further on. I can take 2 by 175 and square and 3 by 175, and now I have to determine the sign of this thing, although I know that in this case I do not have to do anything, because it is either plus 1 or minus 1, and in any case it is going to be 1, because after all it is squared, but still it is good to check once. So, in order to check whether 2 by 175 is plus 1 or minus 1, I have to divide n, that is 175 by 8, and check the remainder. Let us do that. So, 8 dividing 175, 8 2s are 16, and then you see that you get 1 here, 15, and I will write a little non-standard way and write again 2 over here. So, it is 16. So, if I subtract, I get minus 1. So, my remainder is minus 1. This basically means that n, that is 175, 175 is here is equal to 22 times 8 minus 1. Of course, this is true, and this means that it is congruent to minus 1 mod 8. So, therefore, in my case it is 170, n is equal to 175 and it is minus 1 mod 8, and therefore, I know that it is going to be 1, 2 by n is going to be 1 according to that rule. Now, so it is 1, and now I come to 3 by 175 Jacobi symbol, and here I will be using the reciprocity law that is given at the end. In order to do that, I have to check whether m congruent to n congruent to 3 mod 4 or not, where m and n are 3 and 175. So, I have got 4 over here and 175 over here. So, I have got 4 4s are 16 and I got 5 over here. So, now I write 3 4s are 12. So, it is 3, and if I divide 3 by 4, of course, trivially it is equal to 3. Therefore, I have got, well, let me write over here, 175 is congruent to 3 mod 4, and I am writing 3 twice because I am just putting n and m over here, I mean just like this pattern. So, we have got this, and therefore, I know you will have a switch over, but you will have to put a minus sign. So, let me remove this calculation from the board and continue this chain. So, I have got 3 by 175. I know that I have to put a minus sign and put 175 by 3. All right, I have got this one, and 175 is odd. So, no question of dividing by 2. So, I can just go for the first law over here, which tells me to reduce modulo the denominator. I reduce modulo the denominator. If I do that, let us see what happens. So, let us do the calculation over here. I have got 175 and I divide by 3, then I have got 15 over here, this is 2 and 5, 3 8s are 24, so I have got 1. Therefore, I can say that 175 mod 3 is equal to 1, and that is what I will replace over here. This is minus 1, 1, 3, and of course, 1 is a quadratic residue mod 3, and therefore, it is 1. So, I get the value minus 1. So, if we go back few steps, here also we got minus 1 and we have got minus 1 over here. What is the difference? The difference is that in this calculation I needed the factorization of 175 and I do not need it in whatever I have done afterwards by using the properties of Jacobi symbol. Now we come to Solovay-Strassen algorithm, and let us go stepwise first, and then we will try to understand or try to get a feeling that why it works. All right. So, looking at the Solovay-Strassen algorithm, you will see that the input is n, and just as before, there is no point checking with n even, because after all an even positive integer cannot be a prime. So, we will take a positive odd integer n as the input, and after doing that we will choose an integer a. Let me first write n is a positive odd integer, all right, and we choose an integer between 1 and n minus 1 at random. This is also something very important, and that is often not realized, that often people do not realize when people are studying for the first time, that it is a very crucial matter how to choose an integer at random between 1 and n minus 1, but we are not going to discuss that. So, let us suppose we are able to choose an integer at random, and then we calculate the Jacobi symbol of a modulo n and store it in x. So, a is something which is chosen at random between 1 and n minus 1, and then we compute the Jacobi symbol x we do it. Now, if for some reason this symbol is 0, it is possible, because if you go back to the definition of Legendre symbol, you will see that yes, Legendre symbol can be 0. It happens if a is 0 mod p, and so if one of the factors are basically, if one of the when you are factoring out, it is possible that one of the Legendre symbol is 0, then the whole Jacobi symbol will be 0, and if it happens like that, then we will say that n is composite. So, we stop the algorithm, we know that it is composite, but suppose it does not happen. If it does not happen, then basically what we are doing is that we are taking n as if n is a prime number, and we are taking n minus 1 by 2, calculating that and raising a to the power that quantity. And how to do that is again a question, that how are we going to do a raised to the power n minus 1 by 2 modulo n if n is very large, and that is something that we have done in one of our previous lectures, that is we can use square and multiply algorithm. We can do that square and multiply algorithm and do that. So, if we do that, then we get a value of y. So, we get y as a raised to the power n minus 1 by 2 mod n, compute that, and then in the next step we have to compare x and y. If we see that x and y are equal, that is to say if x is congruent to y mod n, then we will say that n is prime, else we will return as n is composite, and that is the algorithm. Now, the question is that why it works? It works because we are essentially using the using Euler's criterion, which says that if P is an odd prime, then A is quadratic residue modulo P if A is congruent to 1 mod P, and it also can be proved that otherwise A raised to the power P minus 1 will be congruent to minus 1 mod P. So, if A is not congruent to 0 mod P, then and P is an odd prime, then the Legendre symbol A by P is essentially equal to this mod P. Yeah. So, if you take A raised to the power P minus 1 by 2 and reduces mod P, you are going to get the Legendre symbol. So, this happens if it is P. So, suppose that n is a prime, then whatever number I choose between 1 and n minus 1, this condition is going to be satisfied. And if n is a prime, if instead of taking Legendre symbol, if I compute the Jacobi symbol, I am going to get the same result. So, here when I am calculating the Jacobi symbol, if n is already a prime, it will be same as just one Legendre symbol corresponding to that prime. I am going to get some x and it is not going to be 0, and then we are going to we are calculating this, which is essentially Euler's criterion, and we are checking that whether they match. If they match, they will match if n is a prime, then of course we come to the end of the algorithm, it says that it is prime. Otherwise, if it does not match, I know for definite that it is composite, because if n were a prime, then this has to be satisfied, otherwise composite. But interestingly, there are pairs of positive odd integers and A such that the Jacobi symbol somehow works in such a way that this condition is satisfied, although the odd integer is not a prime. There are cases like that, and in such cases we will say that that integer is an Euler pseudoprime. So, we will check such an integer in the next slide. Okay. So, Euler pseudoprimes. So, here let us suppose the odd integer that we are wanting to check for primality is 91. I know that 91 is not a prime, but anyway suppose we are checking, and suppose we are using Solovay-Strassen algorithm, which we have seen just before this. All right. So, what we do? The first thing that we should do is to calculate the Jacobi symbol. Let us try to calculate the Jacobi symbol. alright. So, I have got 10, 91. Now, in order to calculate the symbol, let me go back to the rules. So, I have listed the rules over here. So, let us look at these rules. So, 1091, I want to calculate the Jacobi symbol, and I do not want to factorize, because if I am able to factorize, then I am able to know for sure whether 91 is a prime or not, but I am not allowed to factorize. So, I come to the second rule, because 10 is a positive even integer. So, I will write this in this way: 2 into 5 by 91, and then I use the third rule to split up the symbol. So, I get this. Now, I should be able to know what is 2 by 91 by using the first law. So, for that I have to divide 91 by 8. If I do that, and then 3. So, we see that 91 is congruent to 3 mod 8. Because of this, the second line will be valid. So, I know that the Jacobi symbol of 2 modulo n is -1. So, I will write it over here, and then I have got 5 by 91. Okay. And now 5 is an odd integer, therefore, I will go for the reciprocity. In order to check the reciprocity, I have to again do some modular reduction. So, let us do that. So, what I have to do is that first I have to divide 91 by 4. So, 4 dividing 91 this is 3, and then I have to divide 5 by 4, yeah, one. So, in one case we see that the remainder is 3. So, that means that 91 is congruent to 3 mod 4, and the remainder in this case is 1. That means that 5 is congruent to 1 mod 4. Therefore, we come to the otherwise case here. So, that means I can switch over without doing anything. I switch over without doing anything. So, I have got minus 91 by 5, and then I am allowed to reduce 91 modulo 5. If I do that, I am going to get 1 by 5, because of course 90 is divisible by 5, and therefore, and of course 1 is a quadratic residue mod 5. So, therefore, it is -1. So, I come to -1. So, let us now jump few slides and come to the place of our discussion. We see that the Jacobi symbol of 10 modulo 91 is -1. So, this is what we will check over here in the algorithm. Then we go stepwise of this question whether this -1 is 0 or not, and of course -1 is not 0. So, I come to the loop. Before the loop I calculate this y, and that is exponentiation. So, here let me remove this portion from the board. Yeah, I will keep it over here. So, I check it here. So, I will have A, that is 10 here, and the number concerned is 91. So, 91 minus 1 divided by 2, this is 10 raised to the power 45, and I have to reduce modulo 91. Well, I leave it as an exercise. You can check it with a calculator after the class, that it is going to be minus 1, it is going to be minus 1 if you reduce modulo 91, and therefore, in this step of the algorithm we will find that whatever we have calculated as x and whatever we have calculated as y are going to be congruent to each other modulo 91, and therefore, the algorithm will return n is prime, which is not so, because we know that 91. So, if you take 13 into 7, 13 into 7, it gives you 91. So, 91 is equal to 13, or rather start from the smaller integer. So, it is 7 into 13. So, it is not a prime number, but there is a chance that Solovay-Strassen algorithm, if the random number that we have got is A is 10, then it will return prime. So, we said that the algorithm works, and now after this example one would like to ask that why the algorithm works, and the answer is this last line. What has been found by theoretical studies is that the error of Solovay-Strassen algorithm is bounded above. So, each time it makes an error, and if you are running this algorithm several times with different choices of A, because A is randomized, that probability works out to be very, very small. So, what we say is that if it is so I am giving just one specific value which makes it clear, that it says that if Solovay-Strassen algorithm is repeated several times, let us say 50 times, then the probability that it will declare a number to be prime when it is not is bounded above by 0.158 into 10 to the power minus 12, which is a very small number. So, if you are trying with 91, if you run it few times, you will see that you will get it will show that 91 is not a prime. Just once it may make an error. So, that is the end of today's lecture. Thank you.